Hello everyone. Today I will give an intuitive introduction to Kyber, a lattice-based crypto system selected by NIST for post-quantum key exchange. Rather than going deep into proofs, I will focus on the core ideas, lattices, learning with errors, and how these concepts come together in Kyber. A lattice is simply a regular grid of points generated by integer combinations of vectors. What makes lattices powerful for cryptography is that the same lattice can have many different bases. Some bases are short and nearly orthogonal, while others are long and skewed. Finding a good basis from a bad one is computationally hard, and this hardness is what cryptography relies on. To learn more, you can check the video on lattice cryptography given in the description or in the comment box. Lattice. This slide shows a simple two-dimensional lattice. Even in 2D, you can see how different basis vectors generate the same set of points. Now imagine the structure is extended into hundreds of dimensions. That's where classical and quantum attacks become infeasible. Here the key takeaway is that not all bases are equal. Cryptography security relies on the difficulty of transforming a long skewed basis into a short nearly orthogonal one. This problem remains hard even for quantum computers, which is why lattice-based cryptography is considered quantum safe. This also helps explaining early lattice crypto systems such as the GGH protocol. In GGH, the public key is a bad skewed lattice basis, while the private key is a good short basis. Those are used to solve the shortest vector problem. However, GGH has fundamental design flaws that allow the public key to reveal too much information about the private key, enabling attackers to solve the underlying mathematical problem. Although GGH is a quantum safe scheme, it has vulnerabilities. Regardless, it was an early introduction to lattice-based crypto systems that paved the way to work with learning with error problems. Learning with errors, or LWE, is a mathematical problem based on linear equations with noise. Without noise, solving linear equation is easy. But once we add even a small random error, the problem becomes extremely difficult. Kyber security is built on this exact principle. Intuitively, the noise acts as a mask. Even though the equations look simple, the hidden error prevents an attacker from recovering the secret. This small error is the key ingredient that transforms an easy problem into a secure one. LWE is important because it is secure against known quantum attacks. It has reductions from worst-case lattice problems, and it serves as the foundation of many post-quantum schemes, including Kyber. This makes LWE one of the most trusted hardness assumptions in modern cryptography. Kyber works over polynomial rings rather than the integers. These rings allow efficient computation, small key sizes, and fast encryption. Under the hood, Kyber is a carefully optimized version of the LWE problem adapted to structured lattices. The values are capitalized into the set of functions R2, as you can see on the left. Well, the question is, how does it help? On the white box, the first equation is a higher degree with a high coefficient polynomial equation. For the sake of robustness of the equation has to be that heavy, but it requires heavy computation. So model loop learning error introduced. See how in the second equation the degree of the equation reduced, and in the latter equation the coefficient to make the computation speed faster. I mean in the white box. In the key generation phase, the Alice generates a random matrix a secret vector S, and a small error vector E. Then she computes T. The public key is a T, while S remains private. Notice how the secret key is always hidden behind noise, or you can say error. Bob first receives Alice's public key, which consists of matrix A and the vector T. He then generates a random vector R, two small noise vectors E, E1 and E2, and the secret message M he wants to send. Using the public key and this generated value, Bob computes the ciphertext as a pair U-P, where randomness and noise hide the message. This ciphertext is then sent securely to Alice. On the left, this is what Bob's computation looks like after receiving public key, which consists of A and T. Bob receives the public key and generates his own randomness and error term. He computes two values, U and P, forming the ciphertext C. Alice receives the ciphertext C from Bob. Using her secret key S, she computes V minus U multiplied by S, which gives the message plus a small error. If this error is sufficiently small, Alice can safely remove it, rounding the result. After rounding, she successfully recovers the original message N. From this and ciphertext, both Alice and Bob later can derive same shared secret using a hash function. This figure has been taken from Medium website, and I will include the article link in the description. The purpose of this figure is to explain the mechanism in a very simplistic way without heavy mathematical details. To relate this figure to my slide, we should consider the client side as Alice and the server side as Bob. The private key mentioned in this figure is the same as the secret key in my slides. The term shared key plays a similar role to our message aim. In our case, we also generate a shared secret, but with an additional step. As I explained earlier, Alice, acting as the client, first generates a public key and a private key, and then sends the public key to Bob. Bob, acting as the server, uses this public key to create a ciphertext by embedding the secret in the shared key, which corresponds to IM in our case. This ciphertext is sent back to Alice. Alice then decrypts it using her private key and recovers the shared key, which is later used to encrypt the actual data. Baby Kyber is used purely for educational purposes, not for real-world security. The full Kyber scheme operates over high-dimensional polynomial rings and with large parameters, which makes the equation difficult to follow in a classroom or introductory talk. Baby Kyber deliberately reduces these parameters, smaller polynomials, smaller modules, and lower dimensions, so that every step of the algorithm can be written out and understood. If we compare this with the polynomial ring used in Kyber, shown on the right side, we can see that Baby Kyber uses much smaller parameters. Instead of a polynomial degree modulus 256, Baby Kyber uses a degree of 4. Similarly, the modulus Q is 17 instead of 3329. Because of these smaller parameters, all polynomials used in Baby Kyber, including public key and the error polynomial E, which is a random column vector, have degree at most 3, and all coefficients lie between 0 and 16. These reduced values make Baby Kyber easier to understand and visualize, while still preserving the core idea behind Kyber. As before, Alice generates a public key S along with a random error E. Using this, she computes the public key component T. The result T is a column vector which is sent to Bob together with the public matrix A. After receiving the public key components A and T, Bob prepares his message. He first generates an encryption polynomial which acts like an XOR operation by randomizing the message. On Bob's side, two additional random error polynomials are E1 and E2 are also generated. Before performing encryption, the message polynomial M must be scaled up. This scaling done by multiplying M with Q by 2, which is the integer closest to Q by 2. The reason for this scaling is that the polynomial's coefficient need to be sufficiently large. During decryption, this separation allows Alice to correctly distinguish the message from noise, which we'll see in the decryption step. In Baby Kyber, the parameters are deliberately small, so we can explicitly write out the resulting polynomials U and V, as shown here. These concrete values help us to see how the message is embedded and masked by noise. The important idea is that the noise hides the message from an attacker while still allowing the correct decryption by the legitimate receiver. After receiving the ciphertext data U and V, Alice computes the message polynomial by combining the ciphertext components along with the private key S. This operation reconstructs an approximate version of the original message. By rounding the coefficients to the nearest valid values, we recover the exact message polynomial. This rounding step is crucial because it filters out small errors introduced during encryption. First, we round each coefficient the nearest valid value. For better understanding, the modulo 70 ring is shown as a clock. Rounding can be visualized by moving along with this clock to the closest target value. For example, 7 is rounded to 9 because on the modulo 17, clock 9 is closer to 7 than 0. Similarly, 14 is rounded to 0 since wrapping around the ring makes 0 the nearest value to 14. The received polynomial contains noise, so its coefficients are not exactly the original message value. Since the schemes work over a modular ring, here in this case modulo 17, each coefficient lies on a circular number line. During decoding, we round each coefficient to the nearest valid message representative, either 0 or 9 for this example. This removes the noise while preserving the encoded bit. After rounding, we scale down by dividing by 9, which converts the coefficient back to the binary value 0 and 1. The resulting polynomials directly represents the message bit, Hence, we recover the message. Thank you for staying till the end. To learn more about lattice theory and Kyber, I have attached some helpful videos in the comment or the description box. If you are interested in my work on implementing Kyber with chaos-based encryption for secure image transfer, you will also find a link to my paper there. Thanks again for watching.